Hilbert's fifth challenge was to treat physics like maths, to provide an axiomatization, a set of rules from which all the various subfields of physics could be derived. And you might say, well, obviously we failed at this, because quantum mechanics and general relativity don't gel. We've not even arrived at our final theory. But progress has been made, particularly in linking statistical mechanics and fluid dynamics back to the simple billiard ball model of gases that goes all the way back to the early 19th century in Dalton. In particular, we've been able to show that the Boltzmann equation, the way that the different energies of molecules are distributed in a gas, can be derived from this billiard ball model for quite a long time. And we've been able to show also that the Navier-Stokes equation, so important to aerodynamics, can be derived from the Boltzmann equation. But the first step in this, the derivation of Boltzmann equation from the billiard ball model, only works if you make one key assumption: that atoms don't show a kind of preference for each other, that they don't kind of pair up and prefer to whack against each other rather than whacking against any other atom. And you might say, well, that's kind of obvious, right? And I think physicists were actually happy to make that assumption. I was basically taught at university that this was a solved problem. But actually, it was only last year that mathematicians managed to prove that this was indeed the case. And it took a lot of complicated mathematics to do so. So I think it's really interesting that physics and mathematics, they are very bound together. And yet they do have slightly different concerns. What the physicists are happy to accept, the mathematicians want to put on a solid footing.